Hey, good morning, everybody. Thank you for joining us here for our second in our series of webinars here about soil pH. This one's going to focus more on the economics of soil pH and kind of the cost of nutrient availability. Um, my name is Andrew Hoiberg. I'm in charge of the research and development and technical sales here at Calcium Products. Along with me today, I've got Josh Enderson and Glenn Howell, who are both technical sales agronomists for Calcium Products. They help with all the different trainings and customer support from a technical standpoint, and oversee our trial work and all that kind of good stuff with the company. So, got them on board here. If anyone has any questions or comments throughout the presentation, please feel free to type those into the Q&A box there on Teams. We'll go ahead and get those addressed for you. We also are going to be recording this today, so this will be up on our YouTube page here within the next week or so if anyone needs to revisit any of the information in here. Additionally, we do have this approved for CEU credits for CCA folks. At the very end of the presentation, we'll go ahead and flip over to that QR code that you can scan and get your CEU credits that way. We've got this scheduled for a half hour. The previous one went closer to 40 or 45 minutes, which I expect this one will too. So hopefully you're able to stick around with us. So without any further ado, we'll go ahead and get rolling here. We're going to have just a little bit of overlap with what we talked about on Tuesday. But primarily, these are the kind of the big items I'll be talking about today. Any discussion about the cost of nutrient availability has to start with how soil pH actually affects nutrient availability. And then we'll look more closely at what the improper pH is costing growers. And we'll talk a little bit more specifically about 98G and how the maintenance strategy can be beneficial from a financial standpoint. And then we'll leave a little bit of time at the end if we have it for Q&A. These are graphs that we also shared on Tuesday, but I think they're worth revisiting here. When we look over here for yield potential, nutrient availability, and biological activity, these three things, the yield potential really hinges on both the nutrient availability and the biological activity. That biological activity is what cycles nutrients, through the nitrogen, sulfur, phosphorus cycles in the soil. Those microorganisms are largely responsible for turning some of those forms into plant available forms from whatever they have been applied with as synthetic fertilizers. So there's a lot of interaction and tie-in there between those two kind of things. And of course, one hinges very heavily on the other. When we look at yield potential, starting out on this table on the left, you can see the relative average yield at different pH values, goes up. And this kind of goes back to what we talked about on Tuesday with pH of 7 being the kind of the historical level that we would try and achieve for maximum nutrient availability. Over time, those goals, those targets have been modified with a lot of the Midwestern universities have kind of pulled those back a little bit to 6 or 6.5, depending on the crop and the area. So it's always best to check with your local extension service as to what the exact target pH is there. But most of them are right around 6 or 6.5. And even though that doesn't get us 100% relative yield, it gets us pretty close. And so the amount of money you would spend to get your target from, let's say, 5.7 all the way up to 7.0 is going to not be offset by the increase that you would get in yield. So you have to kind of balance these factors of economics and the money that you're going to spend on a liming application, obviously to achieve the best economic results. So when we look at this nutrient availability, phosphorus is the one that we really place a lot of emphasis on when it comes to nutrient availability and also cost, an ultimate return on that investment. So, phosphorus, when you start getting below a pH of 6.5, you can see that availability really starts to drop off significantly. And then again, as we get above 7 on the other side of the pH scale, that availability starts to drop off again. That's because phosphorus is very reactive in the soil. It likes to tie up with other cations that are in there. iron and manganese being ones that it likes to tie up with on the acidic side, and calcium and magnesium that it likes to tie up with on the high pH side. And that limits the availability of phosphorus. And that's not to say that once you tie it up with certain things from a soil chemical standpoint that it's not available. It's still plants have ways, things that they can exude from the roots, acidic compounds that they can exude to improve the availability of phosphorus. So this isn't to say that phosphorus becomes completely unavailable. It just hinders its availability on either side of the pH scale. Other nutrients are also very important. We talked about aluminum. I won't rehash that again today. We talked about that on Tuesday. But again, phosphorus is really the one when it comes down to dollars and cents. And just to reiterate what we also talked about on Tuesday, we get a lot of pushback from people saying, well, if we're lowering our phosphorus inputs, then we shouldn't have to worry so much about pH. I would argue that the opposite is true, that if we're lowering our phosphorus inputs, we're going to be more reliant on what's already in the soil. Therefore, the soil pH is even more important to have managed so that phosphorus availability can be maximized and get that crop yield, that yield potential maximized as well. And again, the prevailing kind of wisdom behind that, or the theory behind that, is that phosphorus is responsible for acidifying. And we talked a lot about that on Tuesday, so I won't rehash that. But phosphorus in and of itself is not the acidifying agent. It's the nitrogen that does that. So again, just remember that in order for us to access that phosphorus that's in the soil, we need to make sure that that soil pH range is where we want it to be. A little bit more on this, the history of this particular graph right here goes all the way back to the 1940s when they started realizing that soil pH had a massive impact on nutrient availability and nutrient use efficiency. And so this graph was developed back then. And again, you can see that phosphorus is the one that has kind of the smallest window of availability. Other nutrients certainly do as well, especially when you get into some of the micronutrient deficiencies. But one of the issues with low soil pH is that things like manganese, boron, copper, zinc, and then aluminum, like we talked about on Tuesday, can become hyper-available, and that can cause a toxic uptake pattern in the plants that can, again, hinder that yield potential. So this graph or table over on the right is one that we've used at Calcium Products for a long time to help people illustrate, exactly what kind of nutrient use efficiency you're getting at different soil pH levels. And, it's not so uncommon for us to run into areas and fields that are down at, 4.5 or sometimes even lower than that. We've seen some down in the upper threes, which is, just ridiculous to think that we've got soil pHs that are that low. But, as we continue to apply nitrogen year after year after year, or every other year, depending on your rotation, you add that up over the course of decades. And you also factor in the idea that we probably haven't been putting enough liming materials out in those fields. You can see that problem compounds itself over time and really becomes an issue. So, we've only got almost 30% nutrient use efficiency when it's soil pH of 4.5. And, once you get up to 6 or 6.5, again, you're at that threshold where you're getting enough out of it that additional material, liming material, to get it up to 7 is probably not going to offset that cost. But we want to get it to at least 6.0 so we can get up closer to that 80 or 90% nutrient use efficiency. And again, you can see that phosphorus is the one that's mostly affected here. Nitrogen, you can see much quicker rebound as we get, up closer to 6, and potassium even more so. But again, those phosphorus dollars are really the ones that tend to get a lot of focus. But not to say that nitrogen and potassium aren't ones that should be focused on also, because, even if we're at this 5.5 level here, you can see that we're still below 70% of that nutrient use efficiency. And that's costing farmers a lot of dollars, and for the idea to be that, well, we don't want to spend additional money on our soil pH program this year because dollars are tight, the farm economy is down. This is real data, real information that can be shared with those growers to say, arguably the best investment for them to make is in their soil pH management. It's not to put out more nitrogen, it's not to put out more phosphorus, but it's to take advantage of the nutrients that are applied and make sure our soil pH is where we want it to be so that we can access those dollars and return that to the grower. I'm going to kick it over to Glenn Howell here. He's done a great job putting together these slides that have some more economic information on them. So Glenn, go ahead and take over there.
Thanks, Andrew. So kind of following on the trend from the table on the previous slide Andrew just discussed, putting those in terms of an economic comparison using some fertilizer prices that are maybe not representative of all areas, but probably something close to what you might be seeing in your local area today for anhydrous ammonia, DAP, potash, and ammonium sulfate. And putting those in terms of economic values based on crop removal at a given yield of 225 on corn, and looking at what that terms in terms of dollars per acre that NP and K are unavailable for crop growth based on those economic conditions. So at a 5.0 pH, our total fertilizer costs are around $150 per acre, and our unavailable or lost fertilizer dollars are representing about $74 an acre of that total. Kind of keying in again on the phosphorus part of things. At a 5.0 pH, $44 an acre of phosphorus cost that is not being utilized because of, again, of the conditions that pH influences there. Bring it up to 5.5, our phosphorus availability or utilization improves considerably and our cost decreases, but it's still a pretty substantial number. And even at a 6.0 pH, $32 an acre. So again, just trying to focus in a little bit more and put it in terms of real values that, again, growers can look at today and think a little bit more about it. Say, well, maybe a phosphorus application isn't what we want to do, but a lime application is something we want to give a little more credence and attention to than it was a few minutes ago before this conversation happened. So I did this in terms of corn on this slide. We did it also for a couple other crops here. So could ask Andrew to advance the next slide, please. We'll do the same thing for in terms of a soybean scenario. So using the same, again, economic values, again, crop removal, yield goal of 65 bushel for soybeans, $28 an acre for a 5.0 pH, 6.0 pH, $21 an acre that we're still invested in that crop and will be investment for a future but not an upcoming crop year based on soil pH. So again, those are real numbers that are based on the economic conditions that are there. Be happy to share this or work with you on some examples that you'd like to look at more specifically based on your kind of things. We did this again for a corn and a soybeans, and the final slide is going to be based on a wheat scenario, winter wheat scenario. Again, $20 to $30 an acre for a liming cost kind of pales in comparison, knowing that you're going to give those dollars away anyway based on strictly phosphorus availability. And we got some other nutrients are going to be involved and affected as well. Again, maybe that $20 investment seemed like a little bit different scenario based on some of these kind of things. So these are, again, conditions that based on some research that's been done in the past, have been vetted and feel proven over and over, and putting them in terms of today's economics and how that can have an impact on your bottom line.
Thanks, Glenn. Yeah, and I think it's important to mention here too that, and we'll get into some of this yield data from 98G, but we look at putting out our maintenance rates of 98G. We're seeing somewhere in the neighborhood of a 8 to 10 bushel increase just from that season of application, and that's looking at a 200 to 250 pound application rate, and so that can easily make up probably at least half of what we're losing out of here if you factor in the application cost. If we go back to corn here for a second, we're again this particularly works out well at these lower pH values, but we even see benefits of these maintenance applications at 6 or slightly above 6. So being able to factor in, that those lost dollars in return yield from using 98G in a maintenance rate scenario is a very real conversation that folks should be having with their growers, about this, and really kind of getting over the hump of cost per ton versus cost per ton when it comes to liming materials. And those are discussions that your sales reps and us and the technical support team are ready to have with you and your growers. And so, I would just again echo the fact that we've got some great information and data available to help drive those decisions at the farm gate. And when it comes to that application rate, those differences, in terms of how the reality of that plays out, we've got our intern this summer is doing some work looking at a survey with a lot of our customers, and one of the things that we continue to run into, and we have for my entire 13 years with calcium products, is the cost of the product, versus ag lime. And again, we talked a lot yesterday or on Tuesday about the apples to oranges comparison between ag lime and 98G. And when it boils down to it, you use a lot less material with 98G, and you use a different target pH with 98G. We'll show a little bit of that on the next slide as well. But it's not an apples to apples comparison. The state scoring system does not do a very good job differentiating between the two materials. And so this research that Iowa State conducted that you're seeing on this page here was done a few years back in 2018. And what we really wanted to kind of put to bed was this idea that you can use the state scoring system to use equated or equal rates of liming materials to get the CCE value. So to rehash again, on Tuesday, we talked about CCE being the reference point or the calcium carbonate equivalence of a liming material, and that is represented by 100% calcium carbonate. And so, we should be able to take any liming material, put it through the state scoring system, and come up with an application rate that's going to match exactly on this green line that you see here. Now, you can see that none of the liming materials achieve this. And, to say that it would be exact would maybe be a little bit, overstating the relevance of these equations. But we would at least hope that it would trend in that right direction, which we see with 98G. But we don't see that with the two ag limes that were used in the study. One was a good calcitic ag lime, and one was a good dolomitic ag lime, both from central and north central Iowa. So we saw a pretty woeful, underperformance from both the calcitic and the dolomitic ag limes. And, again, we talked about how dolomitics are supposed to have better neutralizing potential because of that molecular weight difference between calcium and magnesium. But what we saw here was at the end of this study, the difference between 98G and calcitic was 0.7 units of pH. And again, we talked about how significant that is on a logarithmic scale, and an entire unit of pH difference between 98G and the dolomitic ag lime. So there was a huge difference in how these materials perform based on that state scoring system. And so that kind of leads us, again, to point out that not only is 98G faster to react, you can see, so this kind of illustrates the very early part of this graph, illustrates the superfine materials that are in the ag limes. But you can see as 98G continues to have more of that fine material, the rapidness of that reaction continues, but it also sustains longer than the other ones do. So for this idea that 98G is just a flash in the pan and then it's all of a sudden gone is the incorrect way to think about it. Because what you have happening here are these coarse particles that take over on the ag limes that don't ever really change the pH anymore after that initial kind of push. So, you really could think of ag limes as more of a fast-acting flash in the pan, because you just get a little bit of activity out of those fine particles, and then you don't get any activity out of those coarser particles over time. But since 98G is made out of only fine particles of limestone, you get not only a more fully rapid, but also a fully sustained reaction that neutralizes more of that pH on a kind of equalized basis than the ag limes do. So I think that's, again, really important to kind of look at. And what this also allows us to do, since there's such a big difference in the pH differences at the end of the study, this allows us to use 98G at a more targeted pH value than it would ag lime. So with ag lime, these application rates really should have been targeted for a higher target pH compared to 98G. And that's really how we recommend 98G be looked at versus ag limes, is you use 98G at a target pH of 6 or 6.3, but you have to target ag lime at least 6.5 to achieve that same kind of pH. And that is really where the difference in application rate comes in, is that we're having to target that ag lime application a lot higher than we are 98G. And so when people push back on the price and the application rates, we have to explain to them that that's the true difference between the products. It's not just taking a ton of one and a ton of the other. looking at the price tag and walking away from it. There's a lot more that you have to consider in that. And we understand that it's more of a technical sale, but we're here to help support that and, provide you with this information that we have to help make that clear to the grower and help them know that they're doing the right thing for their soil pH management. So getting back to our maintenance program that I kind of teased a little earlier, our whole idea here, and this again kind of expands from what we talked about on Tuesday, is we've got a lot of active acidification that we're putting into our soils every time we put nitrogen out there. So we want to be proactive about neutralizing that active acidification. And over the course of time, based on our research trials and based on some modeling that we've done, we've come up with two different ways to look at this. One of them is represented here, and this is what we call the kind of best economic return on the investment of the application, and that's 1 pound of 98G per unit of nitrogen that gets applied. So if you put out 200 units of nitrogen, 200 pounds of 98G would be your recommended application rate to offset that within the season. Now, that's not going to completely offset all of the acidification that could come from that nitrogen application. We do have full neutralization rates. It's more of maybe 1.5 to 2 units of pounds of 98G to unit of nitrogen. But when it comes down to the economics and the return on investment, we find that this 1-to-1 ratio works out the best. And again, going back to the tight farm economy and growers' reluctance to make these type of decisions, we would probably recommend that people are looking mostly at this one as well. And we'll talk more about the yield results here in just a minute. But these lower application rates, can allow more frequent applications, lower rates. It really looks and feels more like a fertilizer application than it does a liming application. Allows for more flexibility, potential for blending, all those kind of things that those lower rate applications are beneficial for. And of course, you don't have to get into the huge rate liming applications that can be troublesome to fit in. So here's what a little bit more about what I was talking about with the target pH values. So when we kind of look at how this lays out and how the economics play out, with 98G, we again get more of that faster reactivity. Ag lime is really a slow build. If you're going to target it up to 6.5, if you're only going to target ag lime to 6.0, this graph would be a lot more like that, and you would never really get it up or over that threshold value during that 4-year application. And we look at this in a traditional liming application window when most folks, agronomists and growers that we've worked with over the years tend to do liming applications every 4 or 5 years, depending on a lot of different factors, availability, farmer desire, all that kind of stuff factors into that. Sometimes it's longer, sometimes it's shorter. But generally speaking, we tend to see it as a 4 to 5 year application window. And so with 98G, we would apply in that same early phase, year 1, and we would get a quicker return to that baseline soil pH, that target. And with that, you would get a yield difference. So, based on those numbers that we saw earlier, the relative nutrient use efficiency and the relative yield potential at different soil pHs, you can see that that's where these differences come in. In year 2, when the ag lime application has achieved that target pH, we're not going to see any difference in years 2 and 3 with the soil, with the yield on that soil pH. We would recommend that you come in with a 98G maintenance rate here after year 2 so that we don't lose any of that soil pH to keep it where it is. Again, that's going to be one of those lower 200 to 250 pound application rates. Depending on what type of nitrogen program is being used to keep that soil pH where it is. And then you get that yield benefit again towards the end of the program when that separation has become evident again between the soil pH values and the 2 liming regimens. So, this kind of lays out that whole idea of using a different target pH for ag lime than you would for 98G. We started back in 2017 doing some yield trials, some rate trials with 98G, and this is really what kind of led us, even though we've had folks that have used 98G prior to 2017 in the same type of manner. Typically, we would see that on lower CEC soils, coarse textured soils where huge application rates are not the norm for anything that they're putting out. but we've since been able to expand this out into our entire geography. And what we saw in those rate trials in 2017 was as you got above 500 pounds per acre, the soil pH would continue to go up, but that yield really plateaued. You didn't see a significant increase in yield above 500 pounds per acre. And so we started looking at, lower rates than that. How low can we go with this and still get that economic return on investment from a lower rate application? So we've got 37 trials dialed into this now. The average application rate is about 250 pounds, just below that. All these trials, it's worth noting, were spring broadcast applications. And so this is an application that was put out in the spring, and we got that yield impact that same year that it was applied. It's not to say you couldn't put it out in the fall. You certainly could do that with the same kind of results, but these were all spring applications. So that just shows you how quickly 98G goes to work in the soil in that year of application. So again, it's right around 8.2 bushel increase. We've seen some trials where the increases have been significantly higher than that, where the soil pH is a little bit lower. But it's also worth noting, and I mentioned this earlier, that the soil pH has a pretty wide range of response here. So we're not just getting response from soil pHs of 5 and 5.5. We're getting them at 6 and even a little bit above 6 in some of these trials. So, in any scenario where you're slightly acidic or, even moderately or majorly acidic, these type of application rates work in all those situations. And again, this is a great way to get growers convinced to try out 98G and to put it out in a time when they are reluctant to spend, $50, $60, $70 an acre on liming applications or more. So this is great data to share with them, and it'll give them some confidence that 98G can help in these tight economic times. Soybeans, we're seeing almost a 2.5 bushel increase. The application rate is a little bit lower, closer to 200 pounds. And again, these soybean response has been I'm not surprised, because soybeans tend to be a little bit more soil pH sensitive than corn does. Corn still has a greater magnitude of response, but nonetheless, we're seeing a profitable response in soybeans as well. So more great information to share with your growers on this. One of the things that kind of gets lost in the discussion of liming applications and materials is the impact that we can have from the calcium that comes from it. We think of limestone as a liming material and something that's going to neutralize soil pH. We don't think of it so much as a calcium source, but it is a great calcium source. But like we said on Tuesday, if you don't have acidic soil, you don't want to put limestone out as a calcium source, because that limestone won't solubilize in the soil without acidity. So you've got to have acidity in the soil for that limestone to dissolve. And that's kind of illustrated in this graphic up here, to where this hydrogen has to be present for that calcium carbonate to break into calcium and carbonate, or magnesium and carbonate in the case of dolomitic limestones. And what happens is that this chemical reaction of the hydrogen and the carbonate turns into CO2 and H2O. So water and carbon dioxide are the downstream products of that reaction. And then what's left over is the calcium. And so we talk a lot at Calcium Products about using gypsum as a soil amendment because of the calcium content. And gypsum does not have the same solubility hurdles that limestone does. So you can put out gypsum and get that calcium benefit, in a wide variety of different soil conditions. So, but again, if you're in an acidic situation where you're putting out limestone to neutralize the soil pH, you're going to get calcium as a benefit of that as well. Higher calcium levels, we won't go deep into that today, but higher calcium levels, from a 30,000 foot view, improve the soil structure due to the high flocculation power of calcium. So it's very beneficial and from that standpoint, and can provide a lot of good soil quality benefits outside of the liming correction. Josh, if you're okay, I'm going to kick it over to you to discuss the maintenance economics here.
Yeah, thanks, Andrew. So what we have shown here are some screenshots from some calculators that we have available. to kind of showcase the economics at the grower level for utilizing these 98G maintenance level applications. This specific example is for using corn. Obviously, you have kind of some current crop prices there, yield goals up in the upper left-hand corner. You have kind of just some basic soil pH conditions. These are soil pH conditions that we typically deal with these maintenance rate applications, like Andrew mentioned earlier. We're also comparing in this specific example to a very high quality ag lime, one that we actually pull a lot of samples from across the US and across the Midwest, where you kind of saw on Tuesday there, where we looked at that ag lime survey map. And you can jump on our website if you want to compare to your local ag lime source. But what we're using here, ECCE of an ag lime to be 73%, that is very high for all the limes that we've sampled across the Midwest. So that would actually push this economic factor to be a little bit lower profit per acre over the 4 years, like you see there at the bottom. What we're assuming here is much like Andrew showed with that graph showing the correction early on in the window, and then offering another maintenance application midway through this 4-year cycle. So you see that that correction there with the 900-pound rate of 98G early on. We're benefiting from that yield increase that we just talked about a couple slides ago, and adding the corn economics to that, current crop prices to that, to get the yield increase benefit in a price per acre over that 4-year period. This is, of course, assuming corn soybean rotation with that maintenance rate in there. 200 to 250 pounds, we're probably a little bit on the high side with that 250 rate being our maintenance rate application, like Andrew mentioned. But again, when it comes to application costs, we're probably being a little bit conservative on an ag lime application cost of $4 a ton and an ag lime product cost at $30 per ton. That's going to include logistics. So really this, for your specific grower, depending on the quality of your ag lime, depending on your logistics costs for ag lime, this $28.50 over a 4-year period for your grower could be drastically on the low end of the scale of what your growers could potentially see from adopting the 98G maintenance rate strategy in their corn or soybean crop rotation.
I think it's important too to mention that these yield increase benefits that we're talking about here are considered additive. So it doesn't say that if you're using ag lime you'll get zero benefit out of it. So these additional yield increases that we're seeing here would be above and beyond what you get for ag lime. So we kind of tear the scale or zero the scale between the two products. And what we're showing here are additive benefits for 98G over ag lime, just so that's clear to everybody. So getting back to, thank you, Josh, appreciate that. It's great information. So looking at, again, getting back to this phosphorus story, we had some folks out at the University of Illinois started conducting some research back a few years ago on 98G with phosphorus applications. I'm sure most of you have probably heard at one point or another in your career that limestone and phosphorus should not be put out together because they'll force an interaction between the calcium and the phosphorus. They were really trying to force that to happen in these trials that they did. And what happened was they saw kind of serendipity happen. They saw the exact opposite type of response. They saw a better increase in soil availability of phosphorus. They saw better uptake of phosphorus. They saw better yield when 98G was applied with phosphorus. And that effect was seen even more so at the lower, even the 0 and the 40 pounds of P2O5. Not so much at the 80 rate, but of course you would expect that to be the case because you're putting out a lot of additional phosphorus. So this particular trial, we kind of went back with them and refined the rates and the applications a little bit. So again, we could try and parse out what the right application rate was and if it supported what we had been seeing in our research as well. So looking at the first graph here, these down on the x-axis here, you see 0, 40, and 80 for the P application rates, soil depth. P availability is shown here. You can see that as the rates went up from 0 to 400, we saw a nice increase in the availability at both the 0 and the 40. And this, even at the 80 rate, we saw, a significant increase in both the 200 and the 400. The 800 still showed a little bit of increase over 0, but kind of hit diminishing returns like we saw in our yield trials several years ago. So this really does help support the fact that our maintenance rates are helping to increase phosphorus availability, even at those low application rates. You're not going to see a huge change in the soil pH, if any, by putting out these low maintenance application rates. But what you will see and what you are seeing is an increase in that availability of phosphorus, which translates out to a better yield for the crop. So looking at the corn grain yield, these results are a little bit less consistent, but again, somewhere between that 200 and 400 pound application rate lies, that economic maximum. And we did see significant increases, again, especially at these 0 and 40. So this helps to support that idea that in low input times or conservative input times, managing that soil pH is the right thing to do to make sure we're getting the maximum yield out of those applications. And again, the phosphorus is the one that we focus the most on because it's the one that's affected the most by soil pH. So again, how is 98G greater than ag lime? There's a lot of things that we've already presented today and on Tuesday in terms of particle size and purity. But those are echoed here as well. Variable moisture content in ag limes and variable spread accuracy. We talked about all that on Tuesday. So if you weren't here Tuesday, you can either come next Tuesday to catch that one again, or we'll have that up on our YouTube page here before too long. Availability continues to be a huge issue with ag lime. We hear this more and more from our dealers every year. That they just can't get ag lime. The production of the quarries is lower than it used to be, or the ag lime pile is not as big as it used to be. So, that just continues to create a headache for customers, with respect to consistency of applications. And again, that's why those 4 to 5 year windows can sometimes stretch out to 6, 7, 8+ years. Because of the availability, and it's just not front of mind for people to worry about ag lime. And that's what we really want to have people focus on with 98G, is get those liming applications in the front of your mind so that we can help overcome some of these hard economic times, and also just take advantage of those input dollars that we're putting into our operations. 98G can obviously be handled and blended like other dry fertilizers. We've talked a lot about that. And then, of course, logistically, fewer trips across the field, no piling, less labor, all those kind of things that are beneficial for your operation. With 98G, one thing I want to point out here, and we kind of talked about it on Tuesday, is we do have VR application equations for 98G that can be used for either the correction or maintenance applications. We've got both of those. Flexibility, fall or spring. We talked about those spring application rates yielding good, results with respect to corn and soybean yields. And again, we're really just trying to get people to focus on more frequent and lower application rates and adopt this maintenance strategy, not only for difficult times like we have now, but also for the foreseeable future. This idea of maintaining your soil pH where it's at versus going on these roller coasters of soil pH every 4 or 5 years really should be a primary agronomic focus of everyone that we're talking to here.